Hi, I'm Ashlyn, and I'm going to teach you, you at the desks, I'm going to teach you about intermolecular forces. First, we'll look at some basic intermolecular properties, and then we're going to look at some intermolecular relationships and some intermolecular forces. So sit back, relax, and enjoy.
Before we get started, we must make some important distinctions. Intramolecular forces are the forces within a single molecule, for example, a covalent bond. But today, we will discuss intermolecular forces, forces between different molecules. And remember, intermolecular forces do not involve sharing of electrons and are generally weaker than intramolecular forces. This is a still of gaseous molecules in a container. The bedazzles represent gaseous molecules, while the paper represents a container. These move freely and quickly with little attraction to one another. The intermolecular forces are the weakest in gaseous molecules as they move quickly and are very far apart. Each molecule is similar to a flight attendant. He or she would have very little time for a relationship as they're always moving around.
The bedazzles in this container show an action shot rather than a still of gaseous molecules. They move quickly around the container with little molecular attraction, further enforcing the weak intermolecular forces between the particles.
This is a snapshot of what the liquid molecules of the same substance would look like in the same container. They have stronger IMFs as the molecules move slower and are more closely spaced. As a liquid, the molecules move freely and slide over one another, shown in this container. And since the molecules are more closely spaced, the liquid occupies a smaller volume of the container than the gaseous molecules, which completely fills the container. And this is a snapshot of what solid molecules of the same substance would look like in the same container. Solids have the strongest IMFs as the molecules move the least and are closer together. This container shows closely packed molecules vibrating in place. Also, solids maintain a fixed volume and shape. Is resistance to flow. Water, for example, has very low viscosity.
And corn syrup has very high viscosity, and it won't flow.
Viscosity is resistance to flow. High viscosity, as exhibited by the corn syrup, is caused by strong IMFs, and low viscosity, as exhibited by the water, is caused by weak IMFs. Corn syrup, or fructose, has more hydrogen bonding than water, causing it to have a higher viscosity.
Cohesive forces are the attraction between particles. Adhesive forces are the attractions between particles and their container or surroundings.
Look at this drop of water that we dyed purple. The water stays on the bubble on the slide because of strong cohesive forces. In this drop of water, the cohesive forces are stronger than the adhesive forces because the water molecules are more attracted to themselves than on the plastic slide. Next, adhesive forces are demonstrated by capillary action. The adhesive forces between the water and the glass are stronger than the cohesive forces, and the water moves up the tube. The strength of cohesive and adhesive forces are determined by the shape of the meniscus, or curve at the top of the liquid. Water is shown on the graduated cylinder on the left. The adhesive forces are stronger than the cohesive, attracting the water molecules to the glass rather than towards each other, causing a concave meniscus or U-shaped curve. Mercury is shown in the graduated cylinder on the right. The cohesive forces are stronger than the adhesive, attracting the mercury molecules toward each other rather than the glass, resulting in a convex meniscus or N-shaped curve.
So now that we've covered the basics, let's meet the hydrogens. What's wrong with your relationship?
Nothing.
Nothing?
Takes a lot of energy to break us up. We're the strongest bond there is.
To recap, hydrogen bonding is when hydrogen bonds to a nitrogen, a fluorine, or an oxygen. It is the strongest intermolecular force. It has a high boiling point and melting point, which means there is lots of energy required to break the attraction. Don't get confused though. Hydrogen bonding is not an actual bond. It is just an attraction between two different molecules. Some examples of these are water and hydrogen peroxide. Next up, we're meeting the dipoles. What's up with your relationship?
Our relationship is pretty strong because opposites do really attract. My positive aspects are attracted to his negative ones, and my negative ones are attracted to his positive ones. But we're still not as strong as the hydrogens.
Darn!
Dipole-dipole forces is caused by the difference in electronegativities between the different atoms of the molecules and the lone pairs of the central atoms. They cause permanent unequal distribution of electrons, causing one side to be positive and one side to be negative. These relationships have relatively high melting and boiling points, and examples include hydrogen cyanide, hydrogen chloride, and iodine monochloride.
These are our typical London dispersions. We see them in everything. For these sad molecules, this is the only attraction they'll ever have. As you can see, it's not much of an attraction. They don't really like each other.
We hate each other, actually.
But you're in everything.
But we have our problems, as all relationships do, but
theirs are probably the worst.
Yeah.
Stay away from these relationships. London dispersion forces occur in all molecules. However, they are the only IMFs in nonpolar covalent molecules. They result from the temporary unequal distribution of electrons. They are the weakest of all intermolecular forces. They have low melting points and boiling points, which means not much energy is required to overcome. These ions are being dissolved in water. Look what happens when a positive water molecule attracts a negative ion.
who needs boys when you have puppies?
And she walks away.
An ion dipole force is the attraction between the negative dipole of the solvent and the cation of the solute, while also the force between the positive dipole of the solvent and the anion of the solute. This force allows an ionic bond to dissolve. The dog acts as the positive dipole, attracting the anion away from the cation, breaking the ionic bond.
Let's take a quick quiz to see what we've learned.
Question 1. Put the three IMFs, dipole-dipole, hydrogen bonding, and London dispersion forces in order of increasing strength. The answer is London dispersion, dipole-dipole, then hydrogen bonding. Question 2. Which type of molecule only contains London dispersion forces? Answer 2. Non-polar covalent substances such as methane and bromine, but everything has at least London dispersion forces. Question 3. In which situation do ion dipole forces occur? Answer 3. Ionic bonds dissolving into aqueous solution. Question 4. True or false? Carbon dioxide, or CO2, has dipole-dipole forces. Answer 4. False. Why? The two elements around the central atom are the same, and their electronegativities cancel out each other, as the electrons are not more attracted to one side of the molecule than the other. Question 5. Which type or types of intermolecular forces are present in HCN, or hydrogen cyanide? Answer 5. London dispersion forces and dipole forces. Be careful. No hydrogen bonding, as the hydrogen is bonded to the carbon, not the nitrogen.
Okay, go! Sorry! Instability of...
No.
No.
Okay, no. No.
How's it going?
Yeah.
Ryan, do you want to switch?
Why isn't it
What?
bubbling?
What? Why is it?
Why isn't it bubbling?
Did you do it sideways?
No.
That was scary. I was like...